Yeah, okay. The recording has started. I'll just give a short introduction. So, hello everyone, and thank you for joining us on a Sunday evening. Uh, Today's talk in Astro Week is by Dr. Bhaswati Bhattacharyya. She is a reader at the NCRA Pune, and her work involves various aspects of pulsar astronomy and transient, like pulsar searching, population synthesis, timing, astrometry, transient searching, fast radio bursts, etc. So I guess we can start. I would like to hand over to Dr. Bhattacharya. Ma'am, over to you.
Sure. So it would have been good to give an in-person talk for me and for you as well. So in this strange mode, I think the more we interact during the talk, it will be better, so that we all get engaged and there is no hurry to finish all the things that I plan to say. It's for you to enjoy the talk, and if you like the subject, I'll be glad. Okay, so feel free to interact. And how are we going to take the questions? Garvit, can you just tell me that?
Ma'am, people are free to unmute themselves and ask the questions if you don't mind.
Okay.
And they can also put the questions in the chat. Anything is fine.
Yes. So I may not be looking at the chat box. So if there is something in the chat box, maybe you can remind me. And
yes, ma'am. So in the middle of the talk, I can tell you, right? That
yeah,
there is a question.
you can tell me, and we can take a pause, or maybe you can wait for 2-3 questions to accumulate, and then we can take a pause and then keep on.
Yeah, sure. That works.
Okay.
That works. Okay.
That will be fine. Fine. So let me start. And I do not know how many of you have actually explored knowing about pulsar. So I will try to give a very basic introduction, and then on that I will build up, and then maybe some of the research that we are doing here, we can talk about that. Okay. So in any place you want, you can interact. Okay. So let me first share my screen. Fine. So this is Sunday evening. So for all of us, since we are giving this time, better to utilize that. So let us see this. You can see is Astron website, right? Containing pulsar animations. Maybe Garbit, you can tell. You can see that, right?
Yes, ma'am. Yes, ma'am.
Okay. So you see, so this is a pulsar rotating, and the beam of rotation, when it is cutting our line of sight, we are seeing the pulses. I will go to the next one, then it will be maybe more clear. So it's like from pulsar, the beam of radiation is coming from 2 poles of the pulsar, and as it is cutting our line of sight, we are getting this lit as pulse. Okay. So this site, these animations with credit, you can use anywhere. If you are giving any talk or you are talking to someone about astronomy, you can use that. Since you are doing this Astro Club, you must be talking to school students and your friends about astronomy. Okay, now I will go to some of the slides, and as I have said, since we all don't know each other and we don't know each other's background, so please feel free to interact, and there is no hurry to finish everything. Rather than that, I will prefer that if we gather something and if we enjoy the talk. Okay. So, and after maybe half an hour, not half an hour, that will be much more, maybe 10 minutes or so, I will take a break and I will ask questions, and then I will proceed. Okay, in that way, maybe all of us will be in the same page. So, you have seen that I have given the title of the talk as Neutron Star Laboratories, right? So, why Neutron Star Laboratories? We will know that in the course of the talk. So in this slide, this is the title slide with many pictures because I wanted to attract you towards the science that we are doing. So this is GMRT. You can see many antennas, and many of you, since you are in Pune, may have visited GMRT and seen it personally, like, or if you have not, you have the, like, you can do that. So GMRT is a giant meter wave radio telescope, and it has 30 antennas, and a signal from all these 30 antennas collected together, and it behaves like a big single dish. And we do science, and specifically I do pulsar science. So we will learn what pulsar is. And here a lot of computing is involved. You can see backend, GSB, GWB, these are some jargons. So DSB is a system which was used earlier, 32 megahertz bandwidth system, and GWB is a wide bandwidth system. And after we acquire data, we have to do a lot of computing to take out the cream out of it. So HPC is required. Now the next panel talks about pulsar research, where you see a cartoon picture of pulsar, which maybe you can, if you browse in internet, you will see these kind of pictures where these are field lines. And by studying individual pulses of pulsar, the second panel where my cursor is, it shows the single individual pulses. And then we can do search and timing of pulsars. We can study binary pulsars. We can see eclipses in the pulsars, things like that. Some of these I will talk about in this talk. So let us first start with our clocks. So all of us have used clocks, and that has certain accuracies, right? So you can look at your clock and see how accurate it can be, okay? And you can consider pulsar as a clock in the sky, which has its own definition of 1 second, okay? So this 1 second that we see, in which the second hand makes a 1 full round, that could be different for different pulsar. And we call that as periodicity of a given pulsar. Okay, so one given pulsar which has a definite position in the sky, like you are sitting in one position in Pune, all of you may be sitting in different positions in Pune, okay, or in other places. So you have a coordinate, latitude, longitude, we call in Earth. So if the pulsar is in sky, it has its own position, and we say, we name the pulsar according to its right ascension and declination. Okay, so a pulsar has its intrinsic period and its intrinsic position. That's what we know till now. Okay, so we see ticks from the clocks, right? One hand of the clock makes a round and then comes back. Okay, you see a tick. Likewise, from the pulsar, you see these ticks. For now, you consider that all the amplitudes, these heights are same. This is not, and this is a property of the pulsar, that each individual tick may have different intensity. But for now, if you consider this is the same, then this is a modified form of your clock where the second is defined in a different frame. Okay, so when do you get ticks from the clock? When the pulses from the pulsar arrive to you. So this x-axis is pulse period. So after distance between one tick to next tick is the pulse period. Okay, fine. So before I go further, do we have any question? Maybe I can take those. Garvit?
Ma'am, there are no questions in the chat as of now. So I think we can continue.
Okay, then I can continue. Fine. So the plan of this talk, I will not get into details of this because this is completely flexible, and we may spend more time on one topic. We may not go to all the topics, or we may. Okay, that will be decided on the like how we interact, how we enjoy, and how much time we take. Fine. So pulsars are called as lighthouses in the sky. So these are interstellar lighthouses. Why lighthouses? You know that when the light from the lighthouses, it rotates and in a given periodicity. So you can consider pulses as lighthouses in the sky. And these are rapidly rotating, faster than the Clinton blender, and very strongly magnetized, very strongly, and it is around 100 billion times the magnetic field of Earth is the magnetic field that you get in the pulsar. Now you will slowly understand why I have named the title the talk as Neutron Star Laboratories, because these neutron stars, which are observable as pulsars, have certain properties which are which are not achievable in the Earth. So you can study how matter behaves in such extreme condition by studying pulsar. Okay. So, and these are neutron stars. What are neutron stars? Now you can ask. I am talking about neutron star from the beginning. What are neutron stars? These are end states of stars, and these are very dense. And you can say that around 2 times in Pune University radius, kind of that, we have many thousand Earth masses compressed. So this is very dense. Okay. Now, the question is how precisely one can measure the pulsar pulse period. So since we all have internet, I will take advantage of that. Disadvantage we are facing, that we are not face to face. So the quality of interaction is better if you are sitting face to face. But the advantage is we can parallelly do many things, like listening the talks and doing some other thing. As long as you are motivated, you will catch whatever you want. So here I will ask you to go to this ATNF Pulsar catalog. The web page address is given here. Okay. So all of you, while you are listening to me, go to this Pulsar catalog and find out the pulsar's name which has the lowest pulse period. That means the fastest pulsar from this catalog. Okay. After few slides, I will ask for response from you, so that you will be familiar with this catalog, and also you will be doing multitasking. As I am in that sense not doing multitasking. I am talking to you, but you have the privilege to do that. So let us do that. So fine. So if you go to this ATNF Pulsar catalog, it is a catalog which lists all the pulsars which are published, its period derivative, and other parameters. Now we will say, okay, till now you have talked about period, you have not talked about period derivative. Okay, so what is the period derivative? So pulsars are very stable. As you can see in this slide, it is written that for this pulsar, pulse period is known to this much accuracy. So this is very stable, but it has a very precise slow down rate. So pulsars are slowing down very slowly. Okay, so that tells you what will be the period derivative of the pulsar. Okay, so that goes in something which we call the timing models of the pulsars. Okay, so by knowing the period derivative and other properties of the pulsar, we can predict when a particular pulse will arrive to us even after 10 million years. Okay, so these are very precise clocks. Okay, and its precision is similar to the best atomic clocks that you know are used for time standards in Earth. Its precision is similar to these. Okay, fine. Now I will go to little bit on early history, and after that I will come back to you on the slowest pulsar. So when are pulsars discovered? So before pulsars were discovered, Vede and Zwicky has proposed that there is this new form of stars that we are talking about called neutron stars. And even before pulsars were discovered, it was thought that it is that rapid rotation of such highly magnetized neutron stars can act as energy sources. Then in 1967, Jocelyn Bell and Anthony Hewish discovered the pulsar, and this led to the Nobel Prize in 1974, though not to Jocelyn Bell, only to Anthony Hewish, which we call it was not justified. Okay. Now, I will come to here. Okay, I skip. So this is thought that these neutron stars are formed after supernova explosion. So that if you are interested, you can read more on how neutron stars are formed, the life cycle of stars, etc. So let me go through this quickly so that we can come to the observational research that we do. And pulsars, I have already told that pulsar can work as lighthouses. We think that these are lighthouses, but this model, when these were discovered first, to come up with this model, one need to have pretty much like imagination, and so this was not very straightforward to think that okay, only two beams are giving us the pulses, because at that point of time people didn't knew that these are magnetized. Okay, fine. Now, what are radio pulsars? We already know that pulsars are rapidly rotating, strongly magnetized neutron star by now. Okay, no, in the sense I have told you that. You have not proved it or something. You have to take it from me. Okay, so now when I say strongly magnetized, you will say, okay, what is the magnetic field? One of the slides says that range, but how does it compare with the different observations that you see in Earth? You see that in your refrigerator it has 100 Gauss. The magnetic field of a bar magnet that you have used for experiments have this range of magnetic field. Earth has 0.5 Gauss. Magnetic field of sun is 0.3 Gauss around. Strongest magnet in Earth is like this, but neutron stars are much more magnetized, much more strong magnets. So this cartoon picture shows that this is a pulsar. You can consider it as a simplistic assumption as a dipole magnet, and these green lines are the field lines from one pole to another. And you can see that this is the axis around which pulsar is rotating, called the rotation axis, and this is the axis around which so this is the axis of the magnet, if we call it as a bar magnet, and these are the field lines that are closed, and these are the field lines that are opened. Why open and closed? These are the field lines in which if the particles are moving, they are having velocity which is less than the velocity of light. If it is more than that, then the field lines are not closed, and these are those field lines. Okay. Now, pulsar is situated somewhere very far from us, and the signal from the pulsar is coming to us, is traversing the interstellar medium and then coming to us. And in that process, the signal gets dispersed because different frequency signals travel in different speed when it is coming to Earth, right? So we need to correct for that. So different frequency signals are coming at different speed. Okay, and the higher frequencies come first and the lower frequencies come later, and you need to correct for that. And this correction is called de-dispersion. So after you observe a pulsar, you need to correct for this effect. Okay.
Excuse me, ma'am.
Yes.
There is a question.
Sure, yeah.
So Diganesh Tripathi asked, ma'am, what is that unseen cone of emission?
Unseen?
In the previous slide.
Okay, yeah, this slide also we have. Okay, very, very good question, very relevant question. What is that unseen cone of emission? Why we are saying it is unseen cone of emission? Is it always unseen? Good. So now you consider that, okay, so if this is a bar magnet, it is rotating, right, around its rotation axis, or the cartoon picture that I have showed you. So there you see there are these two poles. So if you compare this picture with this picture, you see there are two poles, and when this pole is aligning with your line of sight, you are seeing pulse from the pulsar. So in general, the geometry of the pulsar is such that you see emission from only one cone. So you are seeing this cone, but this cone, emission from this cone is not reaching your line of sight. Okay, then you are not seeing this. So you are seeing emission from only one cone. So that's why you will term this cone, the other cone from which you are not getting any emission, as the unseen cone of emission. Now the question is it always unseen? You can see that this thing alpha and beta, two angles are marked here. So you can think that depending on what are the values of alpha and beta, there could be a geometry where you see emission from both the cones. So then this will no longer be unseen cone of emission. This will also be seen. Right? So it is possible for some pulsars you can see emission from both the cones, and in that case you will generally we see an interpulse. Okay, so you will see that there is a pulse from this cone, and when this cone comes to a line of sight, you will see a pulse here, which is in between two pulses from cone 1. Okay, does that answer your question? You can unmute and ask if you have any other doubt. Is it okay? Garvit?
Yes, ma'am. I think it's fine.
It's fine.
We have 3-4 questions.
Yes,
so
you can ask those.
Yeah, okay. So the next question is, what causes the release of energy or radiation in the pulse?
What causes the pulse? So pulsar to pulsate, right? So
Yeah.
Why pulsars are pulsating? So this is a very big question, and this answer to this question is not very clearly known as of now. But it is thought that the particles that are moving through these open field lines, they emit synchrotron emission, curvature synchrotron emission, which is giving rise to this emission from the pulsars. Yes, next question.
Yeah, the next question is by Varun Rajesh. Why the magnetic field is tilted? Is it like Earth?
Why the magnetic field is
tilted with the rotation axis?
Okay, so why basically the question is why there is an angle between rotation and magnetic axis, right? So, yeah. So this is I can say that this thing that I have drawn is like just to show you that these may or may not, like there may be different orientations, different geometries possible for seeing pulsars, right? So it could be tilted. There are some pulsars where we see very wide profiles, and we say that this is because rotation and magnetic axis are almost aligned. Okay, so not necessarily that magnetic field will be tilted. It could be tilted, it may not be. So there may be an angle between magnetic and rotation axis, may not be, and you can see that if these are exactly aligned, you will not see any pulse, right? You will see it always. If the rotation and magnetic axis are exactly aligned, then you will not detect it as a pulsar. Though it is a pulsar, you will not detect it as a pulsar.
So only unaligned magnetic field are detected.
Sorry, can you repeat?
So only the magnetic which are not aligned with the rotation axis are detected here.
Yes, which are not perfectly aligned. I will say which are not perfectly aligned. I will, in my talk, I will show you example of a pulsar where you see very small very less of pulse region. Almost always the pulsar is on. Even in this slide, you see different pulse profiles, right? You can see. So there you can see some pulses have very wide profiles, some pulses have narrower profiles like this B1937 plus 21. Here, for the earlier question of unseen cone of emission, you can see the emission from the unseen cone is this one. Whereas for your question, to answer your question, this J2124 minus 3358, here you see almost always you are seeing the pulsar. But there is some off pulse region, that's why you are detecting it. If it would have been exactly aligned, then you would not have detected it. Right?
Okay.
Okay. Fine. So now, Garvit, other question?
Yeah, ma'am, we have 2 more questions.
Yes, yeah, ask me.
So one question is by Adarsh Kumar. How does a pulsar or neutron star acquire such tremendous amount of magnetic field?
Yeah, that happens in the process of collapse. So if you read more on how the pulsars are born, from the main sequence stars, right? So then you will get, so first of all, so there are two things. How do you know that it is this tremendous amount of magnetic field is generated? That I have told you that this has tremendous amount of magnetic field, but you have to convince yourself, right? How do scientists know that this has tremendous amount of magnetic field? To answer that, you have to do something called pulsar timing, which I will try to tell something on that. So doing pulsar timing, you will be able to estimate the magnetic field of the pulsar. Now your question is how this magnetic field comes up, how this is generated. So this is generated in the process of formation of the pulsar. So in the process of the path that the main sequence star takes to generate pulsar, there this high magnetic field is due to conservation of energy and angular momentum, this high magnetic field is formed. Okay. Yeah. Next question, Garvit.
Yeah. So this question is by Somavanshi Devang.
Yeah.
In the diagram of average pulse profile, what
Yeah.
is the reason behind two pulses detected immediately one after the other?
Which one? This one? This D0525 plus 21. Can you please unmute and say which diagram you are saying?
Yes, ma'am. D, E, F,
Yes.
all those.
D, E, F. Yes. Very good question. You are saying why I am saying two pulses detected one after another. I will say, okay, this is not two pulses. This is only one pulse. So this thing that time, so I'm taking D as an example, say for example. So if D is there, I want to replace it in this figure where pulse period versus pulse amplitude is plotted, I will replace each tick by D. Okay. So this full double peak profile is called something like pulse average profile, and these will be repeated. Now we will say how this is created. This will be created by, so this is your, we call the emission cone, and we think that the sparks or charged blobs of emission are oriented in this cone. Like if this is cone, you can say that in a circular, in a like pattern, these sparks are oriented. Now, as your line of sight will cut this cone, you will, depending on how many sparks or blobs of entity it cuts, you will see different kind of pulse profile. So this is a very good question where you actually ask why these observed pulse profile for different pulsar vary from one another. Okay, so this is determined by how our line of sight is cutting the emission entities. I don't know, maybe, yeah, I have a figure here. So if you see the emission cone, these blue points or the black points, these are the emission entities. And it is thought that these are arranged in this manner, right? So this is something called core of emission, and these are called concentric cones. And the emission entities are arranged in this manner. And as these black lines are our line of sight cuts. And different line of sight cuts will give different kind of profile. Like this will give a double profile. This thing, as you see, will cut this one. This component will come, this one, this outer component will come, and this inner, this ripple kind of thing will come from this cut. Okay. Or if it comes cuts a single block, you will get a single profile. So depending on how these emission entities are arranged and how your line of sight is cutting that, you will see different pulse profile. So this is a model which is based on observation of lots of pulsars, pulse profiles at different frequencies given by Rankin et al. Joanna Rankin actually had worked on this on 1993. There is another model called patchy beam model where it says that things are oriented randomly, things in the sense the emission entities. But as of now, this core conal model by Joanna Rankin is more supported. Okay, does that answer your question?
Yes, ma'am. Thank you.
Good that, yeah, good we covered this. Yeah, it will be good if you ask questions and if I answer, then that will keep us engaged, and that is a better way of learning rather than me telling everything. Yeah, Garvit, any other question?
I mean, we have a couple maybe, but would you like to continue the talk and have another batch of questions?
How many you have?
One or two,
Okay.
maybe one. Yeah,
And what is the time? Can you tell me?
yeah, it's 6:36.
6:30. Okay. So maybe we will take another break and take questions. Can
Yeah,
I quickly ask
one
you
thing.
one thing? That the ATNF Pulsar catalog link that I have given you, have you found the shortest period pulsar? Any one of you?
Yes, ma'am. So in the chats,
Mhm.
many people have attempted to
Mhm.
answer that. If you would have a look at the chat.
Okay, fine. I will not get into that now. Maybe after, good that you have attempted that. After the talk, maybe I will look at that.
Yeah,
Fine.
okay.
And get that. Fine. And the answer is around 1.4 millisecond. You must be getting that. So you can ask why this is the shortest period. Okay. Why you do not see any pulsar faster than this, right? What decides that there will be no pulsars which are faster than this? One could be like, okay, maybe there are pulsars which are faster than this and people have not found that. And another answer could be, okay, there are no pulsars, maybe models, the emission models that do not allow the pulsars to spin faster. Okay, so in this way, searching for pulsars which are having very rapid spin period is very important. Okay, now let us get back to this. You have already known about these things, so I will skip this. Dispersion measure we have talked about. We have talked about correcting for dispersion. So dispersion is integrated line of sight column density. Integrated line of sight electron column density, which is integrated 0 to d is the distance to U1 pulsar. Integration of any dl gives the dispersion measure value. Okay, and for each pulsar, as till now we have said each pulsar has a characteristic profile. We have discussed in detail. We have said each pulsar has a characteristic period. We have discussed that it has a characteristic period derivative, and also it also have a characteristic dispersion measure or DM. So as like we are known by our phases or our works, pulsars are known by all these properties. Okay. Now, how will you correct for this DM? So you can go to this guide. This is a this Pulsar Search Collaboratory what I say help material, which you will where you will see this is very nicely explained. This process of dispersion, folding, like the process of searching for pulsars are nicely explained. So you can go there and read about that more. Okay, so for now, you have to believe me that if you do this correction, dispersion correction, and you will be aligning different frequency. That means you will be correcting the delay in which the low frequency radiation are coming to you. So you will do dispersion, and with the dispersion, you will give input to as input raw data, and output as the output you will get as dispersed time series, and you will then fold that like you fold pieces of paper. You'll fold this, and you will get the average profile where the signal will go up as the and the noise will go down. Right? Okay. Now this we have discussed. So now you have a variety of pulsars, right? And if you plot the period and period derivative of all these, you have around 2,800 pulsars. And if you plot the period and period derivative of all this, you will see that these kind of thing will come. So you yourself, this also can be one of the tasks that you can do in ATNF pulsar catalog, you know. So there, list down all the pulsar and pulsar catalog. Within that ATNF pulsar catalog also, you can have plot tool. You have the plot tool and you plot there, or you get that file to yourself in your PC and plot this period derivative, or list down any parameter of the pulsar and see what are the significance, how they are distributed. Okay, so here you see that these black dots are the normal pulsars, and there are other varieties. I will just talk about this normal pulsar variety, and this variety, this purple part is the millisecond pulsar, which are faster and mostly in binary and very stable. Okay, so millisecond pulsars are thought to be originated when it normal pulsar die and it comes to somewhere we call this you can see after this line there is hardly one pulsar. So this is called pulsar graveyard. So normal pulsar die and come here. That means it slows down so much that it is not able to radiate any energy. It comes here, gathers a companion, spins up, accretes matter from the companion, spins up, and is visible as the millisecond pulsar. So this process is called recycling, and millisecond pulsars are thought to be born as recycled pulsars. Okay. Now, in this way, you will say all the millisecond pulsars should be in binary, but that is not the truth. In practice, you see few millisecond pulsars, though less fraction in isolated systems. How? We think that some kind of system called black widow systems are bridge between this binary and isolated millisecond pulsars, and we have discovered one such system with the GMRT. So pulsars can be used as tools. They can be used as timekeepers in the sky. I have already discussed that. They can be used as sensitive gravitational wave detectors. They can probe matters in extreme state. Because they are in such extreme state, they can be used to probe matter in such extreme state. Different, like there can be binary pulsars, there can be pulsars in globular cluster systems. So investigation of dynamics can be done, and also one can probe space-time, one can probe interstellar medium. Okay. So this is top 10 pulsars from my list. You can go through this. I have listed this pulsar, but these may be like biased or maybe because of my opinion. So you can go through this and choose your favorite ones. Now I will tell something on search of pulsars, which I am also involved in. Some of the results that we are having, you can see that. So how do you search for pulsars? We already know one pulsar have its characteristic DM, period DM, that is dispersion measured, and you have to correct for that. Periodicity and periodicity derivative, we call that as acceleration. And especially for binary objects, you need to correct for that. Here I don't have scope to explain how this relates to acceleration. Maybe you can read the handbook of Lorimer and Kramer if you are interested to know more on pulsar search. So these references where you can read more are written here. Okay. So pulsar searching is very much compute intensive. As you can see, these are 3-dimension. We have to search in 3-dimension, and each dimension you have a very large grid. So this is very compute intensive, and we have to record very high time resolution data. As you have already seen that 1.4 millisecond is the fastest pulsar. So if the fastest pulsar is 1.4 millisecond, then within that one pulse bin, you need many pulses, many samples while observing to detect that. And you cannot assume that that is the fastest pulsar. People are trying to discover if there are any sub-millisecond pulsar. Okay. So, and data volume is very large. We are, and it is increasing with wide bandwidth facilities, high time resolution observations, etc. Analysis is very compute intensive, and we are recording lots of data in very small time, and it is practically impossible to crunch pulsar data on single like desktop computers. So what we do is use high performance computers and lot of time. So there are two different approaches for pulsar searches. One is targeted search, another is blind search. Targeted search is you have some idea of where it will be, which you are using and seeing that it is there. And blind search is where you do not have any a priori idea on where it could be. Fine. So we have been involved in Fermi-directed targeted search. So we have started Fermi-directed targeted search in GMRT. What is that? Fermi Gamma Ray Telescope. You may have heard of, or you can Google and find out more on this. So they make a list of the gamma ray sources, unidentified gamma ray sources in the sky, and then unidentified in the sense unidentified with any known source class. And we point our telescope there and we search for radio pulsations. So that has been very successful in survey with the GMRT, and we have discovered a bunch of pulsar in Fermi-directed survey. And then blind survey, where you do not have any information of where pulsar could be, and we have this GMRT high resolution southern sky survey for pulsars and transients, where also we have discovered 24 pulsars. So in this Fermi director, so I have some materials here which you can see later. And then in Fermi directed searches, we have different facilities all over the world who are targeting, and we are coordinating the sources among us. GMRT is the low frequency facility, and the pulsars have steep spectrum which has higher flux density near the lower frequency, so this is benefited. Okay, so we have discovered quite a few pulsars, and with this Fermi directed search effort, the number of pulsars has increased almost 1/3, so number of millisecond pulsars especially. Okay, so as I have already told, this is very compute intensive, and one of the pulsars that we have discovered in the Fermi directed search is this so-called black widow pulsars, which are transition between isolated and the millisecond pulsar. These are thought to be, though there are other propositions as well. Okay, so here you can see that this is the companion and this is the pulsar. When the emission from the pulsar is blocked by the companion, you don't see this. This LOS2 and LOS1 and LOS3, you see the pulsar. Okay, so here the pulsar is eclipsed. But it is seen that the eclipse duration is very high, and it is not eclipsed only by the companion, also by the companion wind. So these shows some of the discoveries that we have with the GMRT. And this is this plot I was saying in one response to one of the question is, you see very wide profile, right? I should say that these plots phase aligned radio and gamma ray profile. So when we discover the radio pulsations from these pulsars, we again fold the gamma ray photons from Fermi-lat, and then we detect the gamma ray pulsations also from this. And here I have plotted the phase aligned radio and gamma ray pulsation, and you see almost no of pulse region here. Okay, very wide profile, and this is very interesting millisecond pulsar. And here you see this is the this is very strong in gamma rays. And here in this plot you see this is the gamma ray intensity over time, and you see that only we know you don't see that here. We know only 3 millisecond pulsars has higher gamma ray luminosity than this, and we have detected gamma ray photon at very high energy for this millisecond pulsar. Okay, so now you will ask why we need MSPs, why we need more MSPs. We already have some 437 or something. Why we need more? Because it can contribute to International Pulsar Timing Array to study gravitational wave background, or individually the millisecond pulsar can be in special evolutionary phase, as I've said this black widow pulsar, or there can be some pulsar which are millisecond pulsars which are transitioning from low mass X-ray binary to millisecond pulsar stage. So this gives the discovery of millisecond pulsars and different surveys and the frequencies. Now I'm coming to the blind survey, and I have already told that we have discovered 24 pulsars, and there are fast millisecond pulsars, and there are some transient source called rotating radio transients. We have discovered 3 rotating radio transients. Okay, and this is the some of the pulsars that we have discovered with the GMRT are listed in the table. Important is this flux density column. We are discovering very weak pulsars. So probably we are probing a different luminosity distribution with a very high sensitive telescope. So these are, as I was talking about, these pulse profiles from, that was from one of the pulsar handbook. But here we see the pulse profiles from our very own discoveries with the GMRT. And you see here also varied kind of pulse profile. Okay, so these surveys that we are doing are ultimately leading us to something called SKA, square kilometer array, which will be discovering a lot of pulsars and millisecond pulsars. So how we are doing with time? What is the time?
6:50.
6:50. Okay, so maybe I will take few questions. Do you think that will be wise, or I can? So how long we have till 7, or
Yeah, like 1 hour we decided, but it's fine like if we do a little more. And we have 2-3 questions, so we can have them.
we have 2-3 questions. Okay, then let me do one thing. Let me talk about pulsar timing for 5 minutes, and then we will take questions and conclude. Okay? Does
Yeah,
it
okay.
sound reasonable? Okay,
Yes,
let us
ma'am.
do that then. Fine. So what is pulsar timing? So I was telling that I have told you that pulsars are very strongly magnetized. How do you know? How do you know the period and period derivative of the pulsar so precisely? All of you must have gone to 18F pulsar catalog and seen that we know this so precisely. How? So the key is pulsar timing. So how to measure how long is the second of your pulsar watch is the way is pulsar timing. So what we do, you observe the pulses with a telescope, disperse, do online folding, make the mean profile, and from that do timing. Okay, and after timing, you generally get this kind of plots which shows that pulsars are having kind of white noise. If this kind of plot you see, that means you have taken care of all the other artifacts and you are getting the actual parameters of the pulsar. So this is how you will now come to this precision. Okay. So after doing timing, you get these like more precise position. So these were discovery position and these were your timing position, which are more precise and more precise frequency derivative, I mean all other parameters. And also as a derived parameter from period and period derivative, you can get the magnetic field, the spin down energy loss, and all other things. Okay, you see the magnetic field is there. So these two pulsars have different magnetic fields. So from a TNF catalog, you can study those. So now I have talked about the pulsar timing array, right? And you don't know what that is. So if you see we are there, this is the Earth, and say there is some gravitational wave source sitting here, and the signal from pulsar A and pulsar B both are traveling through this gravitational wave sources region where it affects and then coming to you. So the time at which it is reaching you will be shifted by very small amount, but it will be having a pattern. Okay, so by studying that you can detect gravitational wave with the pulsars. And the pulsar research in last 50 years have led to very good like new paths of avenues to explore, and you are free to look at all these. Now I will conclude here. Okay, and then I will take your questions. Garvit, you can maybe coordinate and
Yes, ma'am.
yes.
So I'll ask the question. So there is a question by Shinde Rajat. Rotating charge causes magnetic field. If neutron star is made of only neutrons, where are the charges?
Okay. Oh, you are saying if what happens is.
So he's asking that since magnetic field is caused by charges, rotating charges, then basically since it's neutron star is made of neutrons, neutral particles, then how are you seeing magnetic field?
So if you study the neutron star, so neutron star have different like in the outer layer of the neutron star, some free charges are there, which are causing this thing. It's true that it is mostly constituted by neutrons, but there are free charges which are there in the what we call neutron star has core and crust. In the crust it has, and there it causes a vacuum gap. Like there are different models. I have not included that here because that will be a little bit. So yeah. So this vacuum gap model of pulsar radiation, if you refer to this journal, so this is a little bit advanced. This gives an idea on how actually pulsars radio radiation are coming. Okay. Yeah, we can take the next question.
Yeah. Are a symmetrically distributed emission always feasible?
Are
Symmetrically distributed emissions.
symmetrically in the sense, why symmetrically? Maybe who has
Ma'am, actually, I forgot to write about component. In one of slides, you mentioned about symmetrically distributed emission components. So,
symmetrically distributed emission components.
yes, ma'am, in the earlier slides.
In the earlier slides, okay. I am going there. You can tell me where to stop. Are these ones?
Ma'am, before that,
Before that?
yes, ma'am.
After this?
Yes, ma'am. Here. Yes, ma'am. Here. Ma'am,
This one? This.
No, ma'am. After that. Yes, ma'am.
This one is PP dot diagram, right?
Before that.
This one, okay.
No,
This
ma'am.
one?
Before that slide, ma'am.
This one.
Ma'am, yes, ma'am. Here you have written about symmetrically distributed emission components in the diagram.
Oh, okay. So you was what is your question then? Why it is symmetrical?
Ma'am, I am asking, is it feasible always?
Okay, so a good question. And how I know? First of all, like I am saying, symmetrically distributed emission components. A pulsar is somewhere in the sky, and I am observing here the profiles. How I can say that these are symmetrical or asymmetrical or anything, right? About it. So I must be having some observational clue on based on which I am saying this, right?
Yes, ma'am.
Right. So if you go to yeah. So I have, let's say I'm just going to the first, yeah. So this plot that you have, so this plot plots the single individual pulses that are detected from the pulsar, from one individual pulsar. Okay, so that is a strong pulsar. That's why you are getting this upper panel is the average profile, but below you see the individual pulses.
Yes, ma'am.
Now you call what this track is, you call it as drift band. I will mention that this x-axis is pulse phase and y-axis is pulse number. Okay. So this where you can see my cursor is this cut is one individual pulse, right? And we say that this gray point to the second gray point on the same line will give when your line of sight cuts one spark to another, right?
Yes, ma'am.
Corresponds to that. So observationally, what we are finding is we are seeing this kind of behavior of the individual pulses. So by seeing that this this spacing is always same, there are pulsars where we have seen multiple such drift bands, but the spacing is same. So that tells us these are equispaced emission blobs. Okay. Then there are theoretical models which can say how why these spacing will be maintained, right? What kind of electric field and magnetic field combination can give you this orientation of the sparks? So there are theoretical models which can reproduce that, but observationally we see these kind of things which proves that these thing exist. That your question that okay, how can this symmetry be maintained? Not only that this symmetry is maintained, you can see that you can say okay, then outer you can see that this is very strong drift band, strong single pulses. I will not use jargons. Some single pulses outside and inside these are weaker, right? How these are happening? So
Yes,
we
ma'am.
say that there are two concentric rings. So if your line of sight is cutting the outer ring, you are seeing the bands here. Where you see the separation between two bands is little bit different than you are seeing in the inner cone. So there are two concentric cones and your line of sight cutting that is creating this kind of individual pulse patterns. So based on these observational evidences only, people have proposed those kind of models, right? So these are
Yes,
supported. So it seems strange, but this is true. Okay, so this symmetrical distribution is there. Okay, did I answer your question? This is a very good question. Maybe you can read more on this. Okay.
Yes, ma'am. Thank you, ma'am.
Next question.
Shashwat, is your next question also answered about unsymmetrical distributed emission?
Yeah.
Yeah, okay. So next question by Neev is,
Yes.
what is the current status of detecting the nanohertz gravitational waves from pulsar timing arrays? Would there be enough data to detect them soon?
Currently, it is not detected, as you can see. So there are different pulsar timing array we call PTA efforts going on. So it's been one is nanograph we call that is led by the American team mostly, and then European pulsar timing array and also Australian pulsar timing array. Recently, Indian pulsar timing array has also joined. So the thing is that people are trying and they are giving different reports. If you are, I should say, limits of detection. But as of now, there is no detection. And so it is claimed that if you have more number of pulsars in the array, then you can detect that the same signal of gravitational wave signal of same strength with more number of pulsars more quickly than less number of pulsars. So discovering more pulsars that can be added to PTA is like beneficial, and we have the millisecond pulsars that we have discovered are getting added to PTA. So those, like, not only us, for other surveys also this is happening. So with more number of such pulsars, probably, but one catch is that the pulsar timing, after discovery only, you don't get very precise pulsar timing. You need to time it. That means you need to get this very regular TOS and time it for a very long time to make it suitable, so that your this we call residual should be sub uh, obviously sub microsecond and maybe nanosecond. So the better you know a pulsar, it will act as a better clock, right? And for gravitational wave detection, you need most precise clocks will be good. So you need to time the newly discovered pulsar for very precise timing of the newly discovered pulsar will add to this. So as of now, I will say that this is not detected, and it will depend on how efficiently this has been done and how strong that source of gravitational wave is. Okay, yeah. Next question we can take.
In the chats, we had these questions. But if someone has any other question, then feel free to ask right now.
Is there any electric field there in pulsar?
Yes, obviously, if there is magnetic field, there will be electric field, right?
Then only magnetic field is more powerful there.
No, I will not say only magnetic field is more powerful. If there is a magnetic field, there is an electric field, right? So when we are talking about magnetic field, we are not talking about electric field.
Okay.
Right? Yeah. Any other question? Feel free to ask question here. Maybe having some more time, yeah.
There's images in this current slide is there, right? Purple and blue. Is that graphical, or does it really emit in that color?
No, this is graphical, yeah. This is you can see this is not an image that I have made. I have taken it from somewhere, and this is a catchy image, but yeah, no, it doesn't emit it. So we need to do a lot of hard work to like observing pulsar with telescope and getting these kind of plots and searching and all. Yeah, so many things are there. I thought of keeping a catchy picture. Yes, thank you. Yeah. Any other question? Yeah, you can unmute and tell. If I want to say something, I can check. I have mostly covered these things. And since you are recording, you will be having this slide, so you can go back to the references as needed. And Garvit, maybe you can also send me a copy of the recorded file.
Yes, ma'am. We upload it on our YouTube channel, so
Sure.
available.
Yeah.
We have another question. Is it possible that the lone MSPs had a companion that was kicked out?
Yes, good question. First of all, the fact that I am saying that all MSPs are born in binaries. So that is why I am saying that, because that is a way to explain how the MSPs are born. But has anyone seen the MSPs born? Like this path of coming through the death line. So the closest one has seen is some pulsars, some millisecond pulsars, which were previously seen as X-ray pulsars. So some low mass X-ray binaries were seen to be converted to radio millisecond pulsars. So as you say that, so these radio pulsars are thought to be rotation powered. That means they are getting powered by their rotation. You can go to maybe some of this book, maybe the Pulsar handbook, and see what are rotation and accretion powered pulsars are. So these are rotation powered pulsars, and the X-ray emitting pulsars are accretion powered pulsars. And closest we have seen is this transition from rotation powered pulsars to accretion powered pulsars. Okay. So these are called transitional millisecond pulsars, and right now only one we have discovered with the GMRT. So there are 3 transitional millisecond pulsar, and right now this one that we have discovered with the GMRT is right now in radio emitting phase. Other 2 are possibly right now in X-ray emitting phase. So now your question is whether these lone MSPs that we are seeing, how these are seen, these are found. So the support that pulsars are born in binary system can be found from these transitional MSP observations. Yes, it is true that it could be that its companion is kicked off. It could be that it has ablated its companion. So how will you know that if it has like the kind of system that Black Widow system I have talked about, whether it has destroyed its companion or not? You will do pulsar timing, and you will find how much time it will take the pulsar to destroy its companion if it is going in this rate. Okay. So people, like, I am part of one research where it has been done and estimated for some such systems, and it is found that the rate at which it is destroying the companion is not sufficient. Okay, is not sufficient to ablate it at any reasonable time scale. So it keeps us. We don't have the solution of that. It could be kicking off, but then you have to find out some mechanism which kicks off its companion. It is more plausible in globular cluster systems where it is very dense and it has many pulsar binaries, and there it is possible that one binary disrupts and maybe one of the 2 binary combines or some things like that. These interactions are much more plausible in binary pulsar system, not in these kind of galactic systems. One getting kicked off, and also this 20% of these all the MSPs all are created in this process may not be likely. We don't know the answer. Yeah, it's a bit longish answer to your short question, but yeah. So, are there any other question, Garvit?
Not as of yet. Ma'am, would you like to address the shortest time period pulsar in the catalog? Like I think some people got it correct.
Yes, yeah. Let me go to the. Yeah. So you have written in chat box, right? Yeah. Yes. So it should be earlier, right? Yes. Good. So 1 point, fine. You got the period also. Good. So now you have the tools, I would say, to know more on pulsars. And yeah, one of you have asked that is 0034 minus 0534 is shortest. You are the best person to judge that. You compare with other pulsars and see if this is the shortest. It's not, but convince yourself. Okay, so the shortest one is this one, as I think is also written in my slide, but you convince yourself. So it's a globular pulsar, cluster pulsar, and also this will change the moment shorter period pulsar is discovered, and many surveys are doing that. Okay, so those of you who are not getting right answer, probably you are not listing all the pulsars. Maybe you can talk among yourself and see why you are not getting to the this one which has shortest answer. Okay, so some of you all can talk and discuss and find out what went wrong, why you are not getting the correct result. Okay, so okay, and now maybe you are free to find out what is the longest period pulsar, and then you will ask why this falls, does this satisfy the deadline? So you are left with many questions which you have all, like you have the internet now to give you answers, and if you want you can ask me some things. Okay, so if there are no other pressing questions now, we will stop now.
Yes, ma'am. We can end it.
We can end the session.
Yeah. Thank you, ma'am, for taking out time on Sunday, and I hope the audience could learn something new from the talk, and it was great to see some observational aspects of pulsar astronomy.
Yeah. Thank you all for listening. Yeah.
Thank you.
Okay. Bye.
Bye.